All right, GL students, we're going to walk through all the problems on the, well, actually not all of them. These are the problems from the study guide for your Chapter 5 test coming up now on Monday. And I don't think I'm going to have time to do every single one. There were 12 of them, and I want to actually explain them, so I probably don't have time. But I'll do, key ones, and then from these explanations, you'll probably know what to do on the others. Also, all the answers are in the back of the book for these. These are all odd-numbered problems. Okay, so I think what we want to do is skip over number 1. I think probably people are good with that. Let's go on to number 3. So, all right, so here I am. I'm going to do, hold on, let me just make sure I'm recording because I'm not sure if I am. Okay, yep, sure enough, I'm recording. Okay, so here we go. Okay, so number 3. Excuse me, it says you draw a card from a deck. If you get a red card, you win nothing. So let's see. Out of 52 cards, a quarter of them are, half of them obviously are red. So I could have just written, one half here, but you'll see I'm going to need the 52 in a minute. If you get a spade, you win $5. I'm just going to write down what's the probability of a spade. So this is, we'll say that's, well, let me write this a little bit more clearly. Probability that a card is red, this is going to be important information, is a half, which is also equal to 26 over 52. 26 out of the 52 cards in the deck. Probability of a spade. Well, there are a quarter of the deck are spades, and that's 13 out of the 52. It says, for any club I win $10 plus an extra 20 for the ace of clubs. Well, here's what that means. First of all, probability that you get the ace of clubs, there's only one in the deck. See, now that's why I wanted to keep the denominator 52, because I knew I was going to get up to this one where I was going to need to have only 1 out of 52, and I want to have that common denominator. Well, that means you're going to get a different payout for any other spade, or sorry, any other club. So a club other than the ace, that's going to be a quarter of the deck minus that one card that's the ace of clubs. So that's going to be, that's going to be 12 over 52, right? Now there's a reason why I went through all these probabilities to start. Right? You might be saying, back up, what are we doing in this problem? Are we just finding probabilities? Well, no, we're not, but these probabilities will all be important to what we do. The real task, let's see, what is the real task? The real task is to create a probability model for the amount that we're going to win, find the expected amount that we're going to win, and how much would we be willing to pay to play this game, giving an opinion about that. So parts A and B there are kind of giving away something that you need to do at the beginning of all these problems, which is to define the random variable, right? We have this random variable, x, that takes on different values. Okay, so in this case, we should be paying attention to the wording here in the problem. It says, we want to find a model for the amount that we'd win. We want to find the expected value of the amount that we'd win. So that's what x is. X is the amount that you win, okay? And it's a dollar amount. So this is a numerical outcome. That's what a random variable has to have. It has to be, something that comes out to a number. Okay, so what can x equal? Well, let's read this again. It says I could either win nothing, so x could equal 0. X could equal 0, or I could win $5, or I could win $10, or I could win $10 plus $20. So really, X could equal 30 as well. So then, what are the probabilities of these different x values? Well, that's what we already worked out. So probability of winning nothing is if it's red. Now hold on a second. Uh-oh. I missed a detail, didn't I? Oh no, I didn't. No, never mind. Haha, no. I just got mixed up for a second. No, red card is totally exclusive from spade and club. So this really is half the deck. And we can write a half, or we could write 26 over 52, either way. If we get a spade, we win $5. So I'm going to write a quarter. If we get a club that's not the ace of clubs, then we only get the $10. So that's this probability right here. And if we get the ace of clubs, that's this probability right here. Okay, so this is what we call the probability model. Okay, or you could say we wrote out the probability distribution. Okay, so that's done. Now, so for part B, we want to find the expected value. So we'll say, what is the expected value of x? So I think people are basically seeing how this is done, but we can do this easy. This is why I don't want to do question 1, because it's basically the same thing. We're multiplying, and then we're adding, right? So we have a product of 0, 5/4, looks like 120 over 52, and 30 over 52. So we can go ahead now and, grab the calculator. You don't have to do all this on paper or anything. So I'm punching it out here. Okay, so I get 4.13, and I'm going to round it to the hundredths place because this is a dollar amount, so say that's $4.13. We will never win exactly $4.13 on any round of this game, but if we play this game a lot, this will be the average in the long run. That's the meaning of expected value. Okay, and finally they ask us, how much would you be willing to pay to play this game? Well, that might be a personal question, but I hope that the answer is not that you would be willing to pay more than $4.13. I hope you wouldn't put down, $10 each time to play this game, right? Because if this is what you're winning on average and you're paying more than that on average, then on average your profit is going to be 0 or less, and that's not what you want. So I don't know, I guess I would be willing to, I'm not much of a betting man. I guess I would be willing to pay, $1 or $2 to play this game, but it's not very profitable in the long run. I mean, I don't want to, time is money too. I don't want to spend a huge amount of time playing a game if I'm only going to make, $2 every single time. So, I'd pay $1 or $2. Okay. Pausing this for a moment so we can move on. Okay, so we're going to do number 7. Okay, so I'll start writing the numbers in the corner here. That was number 3, and this is number 7. So let's read it. Okay, software company bids on 2 contracts. It's going to make $50,000 if it gets the larger contract and $20,000 on the smaller. There's a 30% chance it'll get the larger and a 60% chance it'll get the smaller. Okay, before we read any further, this looks like a situation where we're definitely going to need to make a tree because there's more than one thing that's going to happen. In other words, we either get well, hold on a second, let me just... Okay, and they're independent, but nevertheless, we'll say they either get... This is for the large. Okay, so either we get the large contract or we don't get the large contract. And then either we get the small contract or don't get the small contract, right? I could probably find a better way to write that. But that's good enough for now. So you see we have 4 outcomes, and really, I don't know which comes first. They don't tell me if the small contract decision is going to happen before the large contract decision, but the way I've drawn it out, large contract happens first, that's fine. Doesn't matter, because it's not in there. Okay, so we got to put the probabilities on our tree. The company estimates there's a 30% chance it'll get the larger contract. So here we go with our probabilities. This is 0.3, which means, of course, this is 0.7. And then there's a 60% chance it gets the smaller contract, so 0.6, 0.4, 0.6, and 0.4. Okay. Okay, so we got all that set up. Now let's read the last sentence. Assuming the contracts will be awarded independently, what is the expected profit? So again, they are telling us what our random variable is. What is the expected profit? So you know then that the random variable is the profit, because that's what we want to find the expected value of. They're asking, what is the expected value of the profit? Okay, so that's what we should write down here. We should say, if I go from here down this road, I get to one profit. If I go from here down this road, I get to another potential profit, and so on. So there are 4 potential profits, 4 potential roads here, paths, right? So we'll do green for the profit here. How much money do I make in this scenario? I got the big contract, I got the small contract. What's the payout? Profit of $50,000 for the big, $20,000 for the small. So this is $70,000 if I wind up here. If I wind up here, I got the big but not the small. That's $50,000. If I wind up here, I got the small but not the big. That's $20,000. And of course, nothing if I wind up there. Okay, so my expected value. Let's set up the, this is my sample space. I could say X is either going to equal this, 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 or this. What's the probability of each? Well, the probability I wind up here is this event has to happen and then this event. So what do we do when we have 2 events that are supposed to happen in sequence and we need the probability of the whole thing happening? We multiply, right? So multiply that and you'll get 0.18. Multiply this and you'll get 0.12. Multiply this and you'll get 0.42. And multiply this and you'll get 0.28. And do these add up to 1? They certainly should, and they do. So now we do the same thing to get our expected value. You guys are pretty familiar with it. We multiply each x by its probability, and then we add that up. So I'm going to have to do that in the calculator. I'll just do this in one shot and see if you get the same thing that I do. Okay, I get 27 for the expected value. I multiplied all these, and then I added up the products. I got 27, and of course, that's not $27, that's $27,000. I should have said $27,000 is my expected profit. Okay, is that all there is? That's the whole question. Okay, so we're going to move on now to number 11. We'll skip another one. Oh no, actually, we'll skip 11. And we'll talk about expected value in one of these other ones. So moving on to 21 with the batteries. Okay, we got a group of 10 batteries. 3 of them are dead. Okay, so this is question 21. 3 dead batteries out of 10, but we don't know which ones they are, and we picked 2 batteries at random, right? So what's going to happen? Either both batteries will be dead, right? Let's say if we get a dead battery, that's a success, and a good battery is a failure. And again, that's ridiculous, but the whole way that we designate success and failure is arbitrary. We can totally switch these. The reason I put it this way is that they mention, the first thing they mention is 3 out of 10. Well, 3 out of 10, or 0.3, can be our p-value here. That's the probability then of success. So the fact that they mentioned this first just makes me think of that as our success. But you can reverse it and it'll be the exact same problem. It's no big deal. So therefore, we could either have, we're choosing 2 batteries randomly. Maybe they're both good, in which case we'd have 0 successes, because it would be 0 dead batteries. Or one's good, one's not, that's 1 success, or they're both dead. And those are the only 3 possibilities, right? So we could say, this is our x, and of course we want to officially define our x, and I'm sure you could think of what to write here. X is the number of dead batteries out of 2 that we select randomly. This is a binomial variable, right? Because they're independent trials. P is the same. Actually, P would not be the same for each one. Maybe this is not binomial, because if you pick a battery, and it's, yeah, this is not binomial, because if you take a battery out of the 10 and it's dead, that or if it's good, that changes the probability that the next one would be good or bad, because there are fewer batteries. It's not some huge endless supply of batteries, it's only 10. So that would significantly change the probability. So this is not some p-value that we can count on. Maybe the first time. Okay. So maybe we need to make a tree here to really think about this. Okay, so we got to make a probability model. It's not going to be binomial. Let's make a tree. You pick a battery. It's either dead or it's good. Okay? Then you pick another battery. It's either dead or it's good. We really got to think about this. Because it's not going to be, the first time you pick it, right, 3 of them are dead. So there's a 0.3 chance, probability, 0.3 probability, that the first battery you choose will be dead, which means this is 0.7. But then, how many batteries are there? Well, if we're here, if we went from here to here, that means we took 1 battery and it was a dead battery. So now there are 9 batteries left, and how many of them are dead? Only 2, right? So the probability that the next battery will also be dead is, from this point to this point, is 2 nines, which means that we have a 7 in 9 chance from here to get from here to here. Okay. Now, same thing here. I picked a good battery. I went from here to here. Now, I went from here to here. Now, I have 9 batteries left, and still 3 of them are dead, right? Now, I should have written that somewhere else. Okay. What I wrote was, of course, the probability of getting from here to here. There are 3 dead batteries out of the 9 remaining. Okay. Okay. So this makes sense. I just got to pause for 1 second. Okay, so moving on. Once again, we have to multiply these probabilities, and we have to say, okay, well, actually, let's just tell you what. Let's shrink this down and move this here. This needs pride of place because we are going to write our outcomes. 2 dead batteries is our 2 successes. This right here is considered 1 success, but then so is this, right? And this is considered no successes. So this, these are our x values. This probability, so this is going to be a little weird looking because I have 1 twice in my distribution, but that's okay. So we'll multiply to get these probabilities. So I'm going to do 0.3 times 2 ninths. And I get 0.067, just rounding that up. I'm going to do 0.3 times 7 ninths. I'm going to get 0.233. 0.7 times 3 ninths is the exact same thing. And then 0.7 times 6 ninths is 0.467. Okay, now we are going to combine these into 1. All right, so watch this. Because they count as the same thing. It's the same value for my random variable. So now here's my real probability distribution. If x is 2, this is still the probability. If x is 1, I have to combine these to say what the real probability of getting 1 is. And it's basically, you know what guys, it's actually, I should even say 7, and let's just round it. Because if this is infinitely many 3s and this is infinitely many 3s, that would be infinitely many 6s. So what I wind up with, amazingly, is the same probability here as I had here. Okay, and does this add up to 1? I certainly hope so. Yeah. Does it add up to more than 1? Oh, no. I see what I did. Yeah, okay, so it definitely adds up to 1. Okay, so what else do we have to do here? This is our probability model. Okay, now we just have to find, for parts B and C, we've got to find expected value, and we've got to find standard deviation. So we'll do that over here. Okay, so expected value, we know how to do that. We've got to do, I've been doing that, sum of the x's times their probabilities. So that's just multiply, 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 and then add across. So we're going to wind up with, so let me just do this. Okay, so it's about, that, okay? No, hold on, that doesn't make sense. Number of expected, really? Hold on, I gotta pause to make sure of my math here. Okay, that looks better. I had something off that I put into the calculator. Okay, so the expected value is this. Okay, so in other words, on average, when we choose 2 batteries out of the 10 with 3 dead, we expect 0.6 batteries to be dead. Okay, so now we do standard deviation of x, and this is going to be, for standard deviation, this one, I can't select that. Standard deviation is similar to this one, but it's going to be, I'll write it down here. It's going to be the sum of x minus mu squared times the probability of x. So we're going to take, in other words, mu just means average, as you know, and this is an average. So we just use this as our mu, okay? So I got to do 2 minus 0.6, square it, multiplied by that. I'm going to write this out. I'm going to do 2 minus 0.6 squared times 0.067. I'm going to do 1 minus 0.6, the quantity squared, times 0.467. And I'm going to do 0 minus 0.6 squared times 0.467. Then I'm going to add them up as per this sigma. I'm going to add up what I get. So let me do that really quick and see if you get the same thing that I do. So this for this one I get, I'm not going to round too much here along the way, 0.13132. .07472, .16812. So I add them together. Okay. So it's about 0.37. I'll round at the end. Okay, so we have expected value of 0.6, and I have standard deviation of 0.37. Okay, that was 21. We're going to do 23, maybe 27, but we might not have time for it. We might have to just let you guys figure that one out. So, and you have the answer in the back anyway. So we'll explain 23 though. 23, you guys just might require an explanation for. So this is 23. You know, also, I think 27 is pretty much the same thing as the batteries. Actually, no, it's not. Tell you what, we'll do 27. We'll do 27. Okay, so here's 23. Given independent random variables with means and standard deviations as shown. So they have x and they have y, and then they give us the mean and the standard deviation. And they say this is 10, this is 2, and for y we have 20 and we have 5. So then they say, what's the mean and standard deviation of 3x? And that just means, what's the expected value of 3x? What's the standard deviation of 3x? Okay, so expected value of 3x. Well, there's a handy fact with expected values that if we have a coefficient in here, we can bring it on out and say this is just equal to 3 times the expected value of x, which is sitting right here. So that comes out immediately. That's just 30. Nice and easy. Okay, standard deviation. Okay, what we should do for standard deviation, because here we can't just multiply this, we can't just multiply it by 3, the way we do with the expected value. So here you're going to have to watch. This is going to require a little trick. We need to remember variance, right? In case you don't remember what that is, variance is the square of standard deviation, which means that the square root of variance is the standard deviation. Same thing, right? Same equation. Okay, so that means if we know these are standard deviations, we might want to add on a column for variance. For x, the variance then is 4. For y, the variance is 25. All I'm doing is squaring the 2 to get the 4, squaring the 5 to get the 25. Okay, so before we can answer this then, maybe we want to answer what is the variance of 3x? And we want to answer that first because we know, here's a particular fact that we're going to use. And I could generalize it, but I'll just show you how it works. The variance of 3x will equal 3 squared times the variance of x. So it's not quite working the same way as, it doesn't work exactly the same way as expected value. Expected value, we can just take this coefficient and bring it right out. But with variance, when we bring it out, it gets squared. Okay, so in our case, in the case of x then, 3 squared is 9, and the variance of x we can see is 4. So that would equal 36, okay? Well, if the variance of 3x equals 36, the standard deviation of 3x, since standard deviation is the square root of variance, would have to be the square root of 36. And we know what that is. It's exactly 6. So this would be our answer for that first part. They're asking us about mean and standard deviation of 3x. There it is. Okay, so let's shrink this down a little bit. Whoops. Didn't mean to do that. Okay. Oh my goodness. Okay. So we'll do another one now. Let's do one, not another one, but also in 23, which is what we're on. What about y plus 6? So what, oh my goodness. Okay. Okay. Finally got it. Okay. So expected value of y plus 6 and standard deviation of y plus 6. Okay, well the expected value of y plus 6 is just the expected value of y plus the expected value of 6. Now here's a funny fact. 6 is a constant. What do we expect 6 to equal? Well, we expect 6 to equal 6. So the expected value of y is 20. And of course, what we expect here is that 6 doesn't change. It's a constant. And we wind up with 26. Okay. Now the standard deviation, of course, as always, is a different story. But it's not too much different, actually, in this case. Because when we do this, now standard deviations don't add, right? Variances add. So we'll show this. The variance of y plus 6 is the variance of y plus the variance of 6. Okay, so we can kind of do the same kind of ridiculous logic here. Variance of y equals itself, and we know what that is. It's right here. Variance of 6. How much does 6 vary? Right? This is like a bad joke. Not at all. The variance of 6 is 0 because 6 doesn't vary at all. It's a constant, right? So this is just... All right, hang on one second. Okay, so the variance of y, then we know is 25. Variance of 6 we know is 0. This adds to make 25. Standard deviation is the square root of that. We're at 5. And notice, that's already the standard deviation of y. So the standard deviation of y plus 6 is just equal to the standard deviation of y. It doesn't change if we add 6 to it, and that makes sense. Adding 6 does not change the variability. All it does is increase everything by 6. So our answer for this one is that we have a mean of our variable of 26 and a standard deviation of 5. Okay, so shrinking this down some more. Hope we don't lose sight of our original table. Okay, so now we'll say this is, what's the next one? X plus y. Okay, so now we do, this is part C, expected value x plus y. I guess I should say variance of x plus y, and we'll do standard deviation of x plus y. Maybe that's the right order to really like write these things in. So this one, expected value is nice and easy as always. It's just going to be the simple sum of x of the separate expected values of x and y, right? In other words, all we have to do is add these two numbers. So it's just going to be 20 plus 10, 10 plus 20, which is 30. Now variances also add. So in a simple situation like this, variances behave very simply as well. And so in this case, the variances are 4 and 25. So we get 29. And so therefore, all we have to do for this is to take the square root of that 29. Okay, done with that one. Okay, shrinking down some more. Let's go to the, oh my God. Gonna let me do it this time. Okay, now we go to x minus y. Okay. This is really good to know. X minus y. Okay, so expected values subtract, just like they added the last time. And we wind up with 10 minus 20, which is negative 10. We have a negative value for our expected value. Variances, now this is a really important fact. Variances do not subtract. Even when we're subtracting x and y, the variances will add. I hope you're reading your textbook. I hope none of this is a complete surprise to you. I hope that you're reading. So this would again be 29, which means all over again that the standard deviation is the square root of 29. We are not going to look at the last part here. We're just going to skip ahead. The distinction between x plus y and x sub 1 plus x sub 2, we may have to get to that in the next unit. So don't worry about that for the test. Okay, so finally we will do number 27 in chapter 16. This is about eggs, and it's not quite like the battery question actually, because they give us the mean and the standard deviation. So we have in a dozen eggs, average number of broken ones is 0.6, standard deviation 0.5. We buy 3 dozen eggs without checking them. How many do we expect to get that are broken? Okay, so we have, each carton of eggs, average for one carton is of 12 eggs is 0.6 and standard deviation is 0.5. This is what we expect, right, from a dozen eggs. So that means that our random variable x is number broken, Broxen, what am I doing? Number broken in a dozen. I don't know how that happened. Okay, so number broken in a dozen. Fine. This is what we expect. Less than 1 on average. Okay. So what we want is the expected value of, okay, so we are going to talk about this distinction. This is not the expected value of 3x, ladies and gentlemen, right? Because we are not taking one random carton of 12 eggs and just multiplying it by 3, right? If we write this, that's suggesting that the 3 cartons would have to actually have the same number of broken eggs in them each, right? This is a subtle thing, but it makes a big difference. We have to treat each carton as a separate, we have to treat each carton as a separate random variable. In other words, I have carton 1 plus carton 2 plus carton 3. Each of these random variables, so this one represents the number of broken eggs in the first one, x sub 2 is the number of broken eggs in the second one, etc. So now I'm finding the expected value of this total and the variance of the total and the standard deviation of the total. Okay, so I might need some room. Not really. I mean, this is not going to be a really big deal, but let's see what happens. Okay, so, and by the way, the variance of my original x, which is just in 1 dozen, would be the square of this. So 0.5 squared is 0.25. That's my variance. Okay, so the expected value of all this. Well, you might say, really, all we're really doing is multiplying by 3 because it's just the separate expected values added together. Yes, that's equivalent to 0.6 times 3, of course. Okay, but it is important that we keep these variables separate, and there is something that can go wrong here. We won't get into all of it, but I'll show you how to do it correctly. The variances add, just like the standard, just like the expected values add. So we wind up with 0.25 plus 0.25 plus 0.25. And so that's 0.75. So to get that, to get the standard deviation, we would simply take the square root of the variance. So this would just be the square root of 0.75, which, I should know that, is approximately 0.866. Finally, it says, what assumptions did we have to make here? So this is actually, we talked about this, the broken egg thing, and what came up in the discussion is, you know, what if the truck was bumpy? If one egg is broken, right, or if one carton has a lot of broken eggs, doesn't that affect, like, what if this is a high number, but they all came from the same shipment? Then maybe that would make this a high number and this a high number. So the eggs as trials tend to affect each other, and the cartons tend to affect each other. So this is not necessarily independent, but we would have to assume it is in order to simply add the expected values and the variances in this like simple kind of way. Okay, so that does it for the chapter 16 exercises. We're going to do some chapter 17 in the next video.